I owe you. I owe you. Chapter 4 deals with language as a carrier of information. Even a short expression as I owe you has a very complicated structure in both the time and frequency domains. 5 phrases are recognizable in the time domain: the initial I, the transition phase from I to O, the O phase, the transition phase from O to U, and the final, slightly longer U phase. A vowel can be characterized as a near-periodic segment of a word signal. In other words, it also must have a line-like spectrum. The longer it takes to pronounce, the more clearly it can be identified. The shorter the period of pronunciation, the less clearly it can be identified. See uncertainty principle. An extremely short vowel would just be a noise. The frequency spectrum shows us that it does not make sense to determine the frequencies over the entire length of the word. Many frequency patterns are interlocking. It is obviously more sensible to analyze individual sections of the word separately. Special techniques have been developed for this purpose. The entire sequence I owe you has been divided up into individual sections which have a gentle beginning and ending, waiting with the Gaussian window. The word begins in the uppermost line and ends at the bottom. The I phase, the O phase, and the transition phases between them can be clearly discerned. Now the frequency spectrum of each section is calculated. This is an experiment which corresponds to the waterfall analysis in the frequency domain. At the top, there are the spectra of the beginning of the word. At the bottom, those of the end of the word. The I spectra at the top and the U spectra at the bottom are clearly identifiable. In the middle, there are the O spectra, with a higher frequency than the U spectra and the blurred transition spectra. Let me now point out the most important results so far. Owing to the fact that the human ear can only hear sinusoidal signals, I will return to this fact later, the following statement can be concluded. Every tone, sound, and vowel have some characteristic frequencies which, just like a fingerprint, are virtually unmistakable. The acoustic recognition of patterns by means of our ears takes place in the frequency domain, because our ear can only hear sinusoidal signals. See the Fourier principle. Glasses, coins, and other solids produce a certain sound when they are clinked. That means they emit, after a transient phase, near or quasi-periodic signals. The same is true of vowels. The spectra of these sounds are almost exclusively characterized by only a few specific frequencies, lines, and thus produce very simple patterns which serve as an identity tag. The first conclusions are: the acoustic recognition of patterns in nature and in technology takes place mainly in the frequency domain. Frequency patterns of near-periodic and quasi-periodic signals for example vowels, are particularly simple because they merely consist of several blurred peaks of different height. Frequency-time landscapes of sounds and vowels resemble beds of nails, with nails of different height. Now the word history as a sequence of vowels and consonants. In the time domain, vowels and consonants can be distinguished quite easily. The shape of the plosives, consonants, are clearly recognizable. The frequency domain of the complete word history, however, does not provide any relevant information. Again, a waterfall representation or frequency-time landscape is needed. Here is the word history as a waterfall representation. At the top, you can see the complete sequence of the word in the time domain. At the bottom, the waterfall representation also in the time domain. The sequence starts with the plosive H, followed by the vowel I. The vowels I and O are clearly distinguishable since they both have a distinctive near-periodic structure. The sibilant S can also be clearly recognized in the time domain, but hardly in the frequency domain. The waterfall representation is used for a frequency analysis in order to resolve the non-periodic and near-periodic characteristics more effectively. These are clearly recognizable in the frequency-time landscape. This type of signal analysis should be used in connection with acoustic pattern and voice recognition in order to be able to identify a specific word by its characteristic sequence of consonants and vowels. The sonogram represents also the frequency-time landscape. The amplitude level is divided into a few vertical layers. Each layer has a different color. Sonograms are used in voice and language research to recognize acoustic characteristics of voices by means of graphic patterns. Now we show a simple system for voice recognition. The exercise is as follows. In a warehouse with tall shelving, the forklift trucks are to be controlled via a microphone. This requires the words up, down, left, right, and stop. Thus, we need a microphone connected with a PC sound card. First of all, we need a database which contains the reference spectra of these 5 words. In order to be able to compare the spectra qualitatively and quantitatively, you should include all 5 reference spectra in one representation. For this purpose, you have to design a suitable system. The module adaptation serves to synchronize the data and to check whether all the signals were recorded with the same block length and scanning rate. That's the trick. Voice recognition by measurement of the correlation factor. The words were spoken one after the other from top to bottom, and the correlation factors for all the reference spectra were measured. Note, every spoken word correlates in a certain manner with every other word, so the safety margin is very small. In the experiment, you will see the importance of the module adaptation. The reference spectra are entered immediately and the modules show EOF, end of file. The spectrum of the word just spoken takes longer to appear because it has to be calculated at first. Only then are the 5 correlation factors calculated. A perfect voice recognition is not possible on this basis. Our brain uses additional, extremely effective methods to recognize a single word distorted in a context. This is where even DaisyLab has its limitations.